Okay. Hello? Can you hear me? Well, hopefully this is online. Okay. So let's get started. This is 1 a.m. Japan time. I would like to start a live stream for this week. So this is a live stream called Houdini Algorithmic Live, a tutorial live stream for Houdini, which I've been doing weekly at some point. And the topic for this week is to create a kind of a 3D bubble simulation like you are seeing it right now. Starting off with some random position of the bubbles and make some clean separations between the bubbles, together with these curved inner wall for each bubble, using more of a fake pressure value from each bubble, using the volume value for each bubble cells. So if you look carefully to each bubble, you can notice that there is some curvedness on each cell, like that. You see there is the wall is not flat but have some kind of a curved wall inside, and that is coming from the pressure from each cells based on the size of the cell or volume of the cell. So that's what I'm going to try to simulate or fake. I mean, the one that I'm going to show you today is not physically, not based on the physics, but more of a visual oriented process. So what I'm going to create today is more of a based on what I saw from the bubble images. So I don't think this is physically correct, but at least it looked nice in the end, like these. And for the bubble simulation itself, how the cell moves, it's based on the algorithm called Lloyd's algorithm, which is to implement the Voronoi centroidal Voronoi tessellation, which I did that previously for 2D plane or 2D surface. I mean 3D surface, but you could also use it for a volume. So I'm gonna show you how you can do that. Use those Lloyd algorithm for volume for today's tutorial as well. So the main topic is to do the bubble cell simulations using centroidal Voronoi tessellation, and how you can use the pressure to create a curved wall for each bubble cell like this for a nice rendering. As I said, this might not be physically correct, but at least visual wise, to make it might look nice. Okay, so that's what it is, and let's do this from scratch. Okay. In the end, I'm also going to share the file with you. You can download from my Patreon page. So if you just want the file, then you can wait till the end when the stream ends. I'm just gonna upload it to the page so that you can download it. If you're interested in process, then please join. Okay, so start with making a geometry node, and I'm gonna start by creating the initial base geometry in order to create a bubble like structure. It could be any closed geometry like sphere or box or any kind of shape, but the sphere could be a good for initial testing. So maybe later I'm going to change the initial geometry to test with other types of geometries, closed geometries. It might not be a good idea to use something like pig head or rubber toy because these have a really thin surface where it's a bit hard to create a bubble, but we could also try that. If we have enough cells, then might be okay with even with these shape. But the better base shape is to have more thick wall like these one or a cube or something like that. So I'm gonna start with the sphere now. Okay, I'm gonna make this polygon 5 for frequency to make a little bit high res. Okay, now first thing first, let's create a initial cell, bubble cell from this volume. Now to do that, I'm just going to use a Voronoi structure. So as you might know, the structure of the bubble is basically just a Voronoi structure. But in order to making the Voronoi cell inflated, it looks like a bubble shape. So the main purpose here is to create the main process here is to create the Voronoi cells first, then make it inflated. Then based on the pressure, based on the volume for each cells, make a pressure value and then pull or push the walls inside to make it look like a bubble. Okay, so that's what I'm gonna do. So let's create a volume out of these base shape to scatter the point inside. The number of point depends how much of a cell you want to create. But since we're gonna use a Voronoi, 3D Voronoi, if you have too much points, then that might gonna be really slow. So especially if you want to do the animation. So let's try to keep the number of cells small for initial test. Okay, so I'm going to create the null node to have all the parameters that I can control later. In this case, a number of cell first, number of bubble cell. Number of bubble cells. Okay, let's say it's from 1 to 100. Let's go with 40 for now. Paste this here so that we have 40 cells inside this sphere volume. Now, what I want to do next is to make each cell and make each surface of the cell to be flat as possible. Right now, the sphere part, you have these meshes, discrete meshes that's being trimmed by the Voronoi cell, a Voronoi wall. What I want to do now is to make these face flat so that it'll be easier for me to do the inflation later. Okay, so to do that, what I'm going to do is to just use a divide node. Then check the remove shared edges. Oops, now that deleted everything. Okay, might be missing something. Okay, I don't really need to do the remove shared edges for inner walls. Just want to remove the edges on the outside of the Voronoi. So if you look at the Voronoi node, there is an option to determine whether if it's inside or outside. I don't want to do the this operation for inside, I just want to do this for outside, which is the surface. So click the divide node, set it to outside, then only the outside surface will be will lose the inner edges and keep the outer edge or naked edge like these. Okay, it's a bit hard to see, so let's normalize this to see how it looks like. Okay, maybe as a primitive. Okay, so it looks like these. Now, next thing I want to do is to, if you turn on the point, you have these points, inline points on each cell, like these. And I don't really want to have these inner points, inline points. I want to make each edge to be straight, so that will be easier to, again, it's easier to create the inflation later. By having these, it's a bit hard to control the inflation with the same quality. So in order to remove those inner inline points, I'm going to write some point wrangle to just remove those points, which is in line. So the rule here is that the point that I want to remove has two neighbors. If this is the point what I want to remove, then it has 1 and 2 neighbors. If it's on the corner, then it has more than 2 neighbors, so those points are shouldn't be deleted. But if it has 2 neighbors, like these points, like this and this as a neighbor, then those points could be deleted. So let's count the number of neighbors by using neighbor count for each point, and if the n count is equal to 2, you can now remove that point. Okay, now if you see it carefully, you can see that the line has been straightened like that. Okay, now the only reason why I did this is to make the inflation cleaner. So there might be a way you don't need to do these steps, but I found out this is the best way to deal with the later process, so bear with me. So remove inline points. Okay. All right. Next. What I'm gonna do next is to have each walls the ID based on the primitive numbers. So if you also look at the inner walls, you have those primitive faces. So I want to have each faces to have its own unique ID, which is going to be used later as well. So what I'm gonna do is to just copy the primitive number, which if you see it on geometry spreadsheet, each primitive has its primitive numbers. I want to pass this number to an attribute as an information, which I can then use it later. And that is also necessary to create a average pressed wall. I mean, in average curved wall for each Voronoi. Now you'll see it later, but for now, let's just copy the primitive number as an ID. So I'm gonna call this pnum as an attribute name coming from primitive number. That's all I'm gonna do here. Okay, next. Next, what I would like to do is to, okay, I think before going into the actual bubble making, let's try to first create a simple simulation for centroidal Voronoi tessellation, which I have also showed you on previous online tutorial live, which was called like weighted centroidal Voronoi tessellation. If you watch it, maybe you know how to do it, but I'll show you. So currently, let's say the point of the Voronoi is a bit more randomized. Like if you uncheck this relaxed iterations for scatter node, you have a bit more randomized point position. Then you have more randomized cell size like these. And if you want to try to make each cell size as same as possible, or same size as possible, as much as possible, what you could do is to move this center of the cell points to a specific position so that the size of the cell becomes close to each other or same to each other. To do that, you can use the algorithm or the process called centroidal Voronoi tessellation, and the algorithm for the implementation is called Lloyd algorithm. And the process is pretty easy. What you just need to do is to first have the center of the Voronoi like this, as a coming from the scatter node in this case. Create a 3D Voronoi like this. Then calculate the centroid of each cell. In this case, like this, let's say this is one of the cell, and by calculating the centroid of this cell, you get each point for each cell, 1 point for each cell, and use that new centroid position as a new center of the Voronoi. So instead of using scatter points, use the centroid of this Voronoi to recreate the Voronoi again. And do that step again and again and again, and in the last you get a similar size of Voronoi cells in the end. So let's do that on the solver. I'm going to connect the initial points to the solver, and going to connect the sphere, which is going to be scattered, which is going to be fractured using Voronoi, to the second input. Then first you create the Voronoi cell, Voronoi fractures, using the mesh input and the points like this. Then next thing you want to do is to calculate the centroid for each cell. So you need to know the attribute for each cell. In this case, you could either use piece or cell PT. Probably I'll use cell PT. That's the point number coming from the point input. And use the measure node to calculate the area per piece based on the cell PT attribute, which will create and I need to calculate the centroid in this case, which will create the centroid information, the center point information for each cell. In this case, this is for cell PT equal to 0, which shares the same center point here, and for cell PT equal to 1, which has another center point like these. So what I need to do is to use those cell center point as a new point information for a new scatter Voronoi fracture. So to do that, what I would like to do is to update the previous point position, which is these, with a new centroid point position coming calculated here. So referring to the result of the Voronoi centroid here, we need to find out the corresponding centroid information, which is stored in primitive attribute. So if by searching for the cell point attribute on primitive, you can get the centroid. So whichever cell point PT you choose, if you are searching for the value equal to 0, then you always get the same result anywhere. So all you just need to do here is to use the function like find attrib val coming from the second input. We are searching for the primitive attribute. The attribute name is cell PT, and the cell PT is actually the PT number of the previous point. Okay, this should give you the search result, one of the search result with these queries, and the search result is actually the primitive number coming from the second input, and there from here you could get the centroid value using prim function. Then if you replace the current point position with the centroid, the distance between each point should become a bit more evenly distributed. And if you repeat this process again and again, you have more cleanly distributed points. As a result, you get a similar cell size for each Voronoi. Now let's check. So if you go back to the solver and play it, you can see, I don't know if you can see it with this live stream, but let me make the point size a bit bigger. Okay. So if I play it, you can see that the point is being distributed cleanly. The distance between each point becomes even to each other. And as a result, by using it as a Voronoi cell center, you get more of a hexagonal surface shape. And if you look at a 3D shape, you get similar size Voronoi cell. And that is really close to what you see as a bubble shape or bubble structure. Okay, so that's the algorithm for centroid of Voronoi tessellation, and that's pretty simple. And the latter process is all about making the bubble-like visuals using more of a procedural process. Okay, so let's do this. Okay, I have some comments. Hello everybody. Have you thought of creating a procedural pipe system sometime on your translation? The random pipe system which would circumvent obstacles and stick to collisions properly, although going on fancy looking. I think you're talking about like something like sci-fi pipe structures or something like that you see on, I don't know, factories or some things like that. Yeah, I love that kind of structures. Would love to try that as well. Yeah. I think I would like that kind of idea. So yes, that's on my list for sure. Okay, so what was I? So let's try to create a visually nice bubble shape from here. So what I want to do here is to try to create an inflation. Now you could always use Vellum, but Vellum is a bit too slow, and if you want to use these like animation together, then Vellum might not be a option because it costs a lot of like processing time. So let's try to do this procedurally and see how this works. Okay, so now that I have these Voronoi cells, which currently is like these kind of shape, moving like a bubble. Next thing what I would like to do here is to try to create the each cell inflated, obviously, and I think I need to do this piece by piece and combine them together to have the average wall positions. So what I'm gonna do is I'm gonna pick each cells from now. For example, pick the cells. Okay, can't click it right now. Oops. Let me save this, reset the viewport. Okay, now I want to pick each cells like this and try to inflate each cell like a balloon. Do this for each cells for Voronoi, and in the end I'm going to get the average point position for each walls to get the average wall positions. And for example, so let's say if you have this cells and you have another cells on the neighbor like this one. And what I would like to do is to create an inflated geometry for this one and this one. In the result, you get intersected like walls on the intersections for sure. And in order to create a curved wall, you need to have kind of a different inflated result for a different inflated strength for each geometry, I think. So probably based on the volume of the geometry, how big it is, you could probably change how much it could inflate or not, and later combine these two intersected walls to have a lerped wall position to give a final result. So for example, if this wall has this much shape And if this cell has a smaller walls, then in the end, if you lerp these two walls together, you might have this kind of a wall shape. Might be hard to explain, so let me sketch. So if you're looking from the side view, say you have two cells. If you inflate one like this one, and if you inflate the other one like this one, you have intersected wall like here. And you want to somehow get the average of these two walls like this, or maybe like that, to have a wall in between two Voronoi cells. And continue doing that with the other cells. You'll have a nice bubble-like wall surface, or inner wall surface. And do the same for the outside. I mean, for the outside, there is no intersection, so you can just use whatever the cell try to be inflated as. So that's the plan, and let's try to do that. So first thing first, in order to create the inflation, you need to have a bunch of points on each surface, and currently there are no points inside the surface. So let's try to create that. And the point, position, and numbers should be shared if you are sharing the wall. So you need to have the same point numbers and same point positions for each inner walls if you are sharing the same wall. So the wall for this cells on here and wall for this cells at this position should share the same point number as well as point positions. Okay, so the best way to achieve that is using the subdivide, I think. I'm going to use the subdivide for each cell to create the inner wall division. Okay, forgot to switch the... Okay, so what was I? So what I was saying is that the in order to have the wall, the intersected wall here for this cell, and this cell, the same wall for this cell here, you need to have the same number of points and the same point positions in order to get the average for each point position to create the curved wall, to get the average wall value. So the best way to achieve for each shared wall to have the same point position and the same points and same point numbers is to use subdivide function. So let's do that. And before getting into it, I might want to fuse the point position before removing the inline points, just in case, because it might not be fused in this the point on the corner might not be fused before, so just to make sure that it's being fused. Okay, it is being fused. So this process might be necessary before removing the inline points. Okay. So let's try using the subdivide node. Okay, and the option that I'm going to use is maybe just using the subdiv cut mul clock is fine. But I'm going to override the weight attribute so that if I increase the depths, what I want to achieve is to make sure the edge stays at its point position. So I want to make sure that I am overriding the weight attribute and make sure the crease weight is like high enough. Okay, and I think I cannot just place this subdivide just right after this whole Voronoi structure shape, because it's just gonna merge everything if I just do this like this. So I need to do this for each cell, I think. So let's do this for each cell geometry. So to do that, I'm going to again promote an attribute like P, so cell PT. Probably I'm gonna use this cell PT based on the point number coming from this output. So for each cell PT geometry, in this case, change this to cell PT, which will get each cell geometry like these. I'm going to subdivide it like this. By doing it, you can keep the number of number of points on each surface the same, and position of the point to be the same position. And the override crease weight attribute is also necessary so that you don't get rounded shape. You don't really want to change the point position on the corner, but you just want to increase the number of points, or just increase the resolutions of each surface constantly. Now you could, by increasing the depths more, you could have high res bubble inflation simulations, but that's gonna make it slower. So I'm gonna keep it at 2. But later I can use the final subdivide as a polish to make smooth again. So simulating with 2 is, I think, is fine. Okay, so it looks like this. And if you check it with other cells, you can see that the number of points on each surface is pretty much the same, and the position also stays the same. So the good thing is that even if you pick this cells or this cells or this cells, the neighbored surface always shares the same point position and same point number, which will be easy to pair each point to have the average point positions later. Okay, so that's the reason why I'm using subdivide. If you use remesh, then the point position is not the same, the point number is not the same, so it's a bit harder to create a lerp or average point position to create a curved wall. So I don't recommend using this, and this is even slower. So I think using subdivide is better in this case. Now, okay, now I did subdivide for each cells. It's time I create the the inflated result. Okay, so to do that, I'm gonna use another for each loop, and if it's possible, might want to use a compile block as well to make it multi-threaded, but not sure if it's possible, so I'm gonna try that later. Okay, for now I'm gonna create another for each loop for each loop. Okay, based on the, okay, not this one, for each named primitive. Do this for each cell PT. Okay, and I think I should bring this pnum, which was transferring the primitive number as an ID, to here before creating the subdivisions. Now I could connect this one here to, again, which is similar to this setup, but now I'm going to do this for each cell. In this case, I'm going to try to create the inflation in this for each node. So where should I start? First thing I want to make sure is that there is a chance, if you look at each cell, there is a chance that I'm going to have another inline points which have two neighbor points. So I'm gonna copy this remove inline points just to make sure that I don't have two neighbors or inline points for each point. And probably I should do the same for this one as well. I'm gonna copy it right here. This might not be necessary, but I found it sometimes you have these additional points inside somewhere around here. So probably this is necessary. Okay, now's the time to think how I'm going to create the inflated surface. Okay, so first I'm gonna try to do is to let me go back to the sketch again and think how I'm going to create the inflated surface. So you have some crystal-like shape like that, and you want to create more of a inflated shape like this one. So and my process here, I mean, there might be a lot of ways to deal with this kind of inflated shape, but my process that I'm going to do is to first get the outline of the cells. So get the path or path information of the cells, and before inflating the surface I'm going to inflate the curve, which is a bit more simpler to do. So just trying to inflate the structure of the bubble like that. And you can do that by getting the centroid of each surface, or yeah, each surface, like this one, on this one, on this one. Or maybe not. Maybe you can just get the centroid of this cell itself. So taking this cell as a volume, you can get the centroid of the volume somewhere on the center, and use this point to move these curve using the vector value from the center to each vertex point position. To create the curved outline like this. Then later, when you get these curved informations, what you want to do now is to fill these curves with some surface, right? So that's where you need to do the inflation or pseudo fake inflation simulations. First thing you could do is to create the minimal surface on top of the curve. Maybe it could be pretty close to the flat surface, or maybe it's being convex or concave shape. And since I want to have an inflated result, you could then push each point to the normal direction. Create a kind of an exaggerated inflated geometry. Do the Laplacian smoothing to make it smoother, or try to make the surface a bit smoothen out, and continue doing this for several times. In the end, you get kind of a similar result to what you get out of the physical simulated inflated result. This process is pretty similar to what you actually do in physical simulations, so but with small steps, small number of steps. So it should be faster, and the result might not be really precise, but you could kind of get the result you might are looking for. So that's my plan. Let's try doing this. Okay, let me look at the comments. Sorry, I don't speak Spanish. Could you switch to view? What kind of case would remesh be better? I'm not sure. In this case, I can't think of any way the remesh work better. So yeah, maybe if you are trying to make a bubble, like in my way, man, I don't think there's a way to use remesh, but there should be a way to use also use a remesh as well. Especially, I mean, the downside of the subdivide is that even if the surface size is small, you get a really high number of points. Doesn't relate to a size of the surface, so that's the downside of the subdivide. So in those cases, remesh might be better, but you need to think of how you could relate the inner wall next to each other, so that you can have the average point position to have the curved wall. So that's the challenge, and I myself couldn't find out the best way, so I'm going with the subdivide. By the way, have you seen the work of Panoply Studio called Tide? It is a combination of several layers of ink and water resembling small mushrooms floating in different directions. Looks awesome. I haven't seen it, but I'm interested. I'll watch it. I hope you allow sending links in comments. I don't know how to enable the links in the chat. I think there's no option to do that. The YouTube just automatically deletes it somehow. Maybe to prevent the spam, I guess. Sorry for that. Well, can you use the same data then to affect how a cell pushes out? Can you use the same data then to affect how a cell pushes out? Yeah, you could. If you know Vex, you could do that using Vex for sure, I think. Okay, so what was I? So I have removed the input. Then yeah, let's try to first inflate the curve. So to do that, I need to have the centroid of the cell first. So measure node, calculate the centroid per, let's say, per piece is fine. Cell PT. So in this case, I'm just gonna have one point information out of this cell, out of this measure node. If you go to the primitive, you see the centroid on each faces, but shares the same value, which is the final value of the centroid of this final piece. So and next I'm going to convert the primitive to a bunch of lines so that I can inflate these curves using the centroid that I've just got here. Now if you use the convert line, all the primitive attribute is removed, like reset it to 0. So I'm going to use the attribute transfer to bring back the centroid information to each cell, each curve. Okay, and so what I would like to bring is this centroid information. And just in case, I'm going to uncheck the distance threshold so that whether it is far or not, you always get a copy of the centroid. Okay, now I might also want to copy the cell PT information, which is this one. This is also an important value, I think. So going back to the attribute transfer, also check the cell PT. Okay, now the cell PT is also copied as well as centroid. Okay, now currently, in order to create the inflation of this curve, you don't have much points to do that. So let's increase the number of points for each line so that you can make a curve. So I'm going to use a resample to do that. Now this resample is pretty important, and the number of points you add on each line has to be the same as the position of this subdivide mesh. So for each subdivide mesh on each edge, in this case you have always 1, 2, 3, 4 divisions. Even with these small lines, you have 4 divisions. 4 divisions here. On the side, you also have 4 divisions. So the number of sampling or number of points on each line is always constant based on a number of subdivide depth. Okay, so if the subdivide depth is equal to 2, then the resample number should be not based on the length, but should be based on the number of segments, and is equal to 4. Or maybe not. 5, is it? No, 4. I'm seeing other points, and that is because I think I also need to check this resample by polygon edge. Okay, I'm still seeing points which I don't want to see. Maybe that's a cache. Yeah, that was a cache. Okay, what was I? So the points coming from this resample and the subdivide mesh should be at the same positions. And if I increase the number of subdivision depths like 3, now you also have to increase the number of resample numbers. In this case, that is equal to 8. So by using this value here, if the depth is equal to 2, that is a power of 2 with a number of depths. So if the depth is equal to 2, that is 2 by 2 equal to 4. If the depth is equal to 3, then that is 2 by 2 by 2, and that is equal to 8. And now the number of resampled, the number of points on the edge, and the number of edge coming from the subdivide is equal. And by doing this, it's easy to relate each other, this one and this one, later. Okay, that's pretty important in my process. Okay, now I'm gonna make this back to 2. Let's also have this depth as a parameter on null controller, in case you might want to change the resolutions of this bubble later. Okay, so bring this and subdivide level. Okay, I think maximum is 3 is fine. Right, now that I have this curve with a bunch of points, it's time to move these curve or simulate the inflation for each curve by using the centroid that's been calculated here. Let's do that. I'm going to use the point wrangle, or maybe I should use a primitive wrangle, because each primitive has its own centroid information. But yeah, I think it's better to use primitive, because I also want to use since I want to make an arc-like inflation, maybe using a sine trigonometry like sine function makes sense in this case. So primitive wrangle arc, or let's name this outline arc or outline inflation. Okay, have you ever thought about using digital paper rather than going back to the whiteboard every time? This would allow you to display directly on your screen what you're doing on tablet while keeping this whiteboard side, not urging you to do anything. Just like an idea like that. Yeah, thanks for the suggestion. Sometimes I do that based on the equipment that I have currently. Now I currently don't have an equipment like that, so like tablet or pens, digital pens. So if I have these, then yeah, I would try to do that as much as possible. Today I just have the analog pen and whiteboard, so please bear with me. Yeah, benefit of using digital pen is that you can save the image as well. So I thought for sure that's better. Is it possible to find that effect just by searching panoply tide on YouTube? I'm talking about the inky mushroom effect mentioned in my previous one. Okay, thanks. I'll do that later. So what was I? Yeah, trying to push the curve. So I'm using primitive wrangle, so I'm going to get each point on each primitive. And loop through all the points. Get the point in numbers. Get the point position. Okay, now I also would like to get the centroid information, which is stored in each line as a primitive attribute, so that's good. So let's create a directional vector value, which is position minus centroid. Right. Now that I have a vector value going from the centroid to each point position, so let's say centroid is somewhere around here, these are the points. So you're now creating the vector like going from the center to each point. And I want to use those vectors to move each point as an arc shape. To make an arc, the best function is to use a function like sine function or trigonometries. So let's create, in order to use the sine function, you need to first create an angle at each point position. And the sine wave is like when the angle is equal to pi, which is equal to 180 degrees, you get the mountain shape like this from 0 to pi, and pi to 360 you are getting the negative value, and the maximum of this wave is 1, the minimum is equal to -1. So what I would like to have is this area here from 0 to pi, and you have a nice mountain like shape here, so I could use this for each curve. So if this is the line that I want to inflate and you have a bunch of points to move, what I want to do is to, from each point, I want to move each point like this, like a sine wave. And the height here can be calculated using this sine wave And in order to determine how much the height is, you could calculate, you could use each point position converted into an angle. So the first point should be 0, the last point should be pi, meaning 180 degrees. The middle one may be 90 degrees, this might be 45, and this might be 135, and so on. So that's what I'm going to try to get here. So what I could do is to convert this I value, I guess. Fit I, which is from 0 to the length of PTS minus 1 to 0 to 180 degrees over pi. Okay. Now I want to convert this angle to a height by using sine wave, which will give you a value in between 0 to 1. If the angle is 90 degrees, then you get 1. Now I'm gonna convert this to a height value by multiplying the sine function by the actual maximum height. Which could be determined by yourself. Okay, now using this, I would like to move the point position. So current point position is pos, and update this by the direction, multiply by the height, and probably also might make sense to use the length of each line as a multiplier. If the length is small, then the inflation should be smaller. If the length is larger, then the inflation must be bigger than the smaller one. So I think it makes sense to multiply with the length of each line. And the length of each line can be get by accessing to rest length, which has been created when you have converted the line on primitive wrangle, these one. So this is the length for each line. So we could actually use this as it is as a multiplier for moving distance or inflating distance or inflating value. Okay, and finally update the point position using set point attrib like this, and let's see how it goes. Okay, not bad. And if I change this, looks like this. So yeah, not that bad. I think maybe I can increase the threshold a little bit more. Let's make this maximum 5. Maybe that's too much. Okay, well, maybe 1 to 1.5 might be better. Okay. This is still low res, but it's fine. We're gonna make it high res later. Okay, so if we look at the end, we're gonna have things like this. So on the intersection, we have a bunch of lines which are going the other directions. So in the end, we need to combine these lines together or get the average of the one that's next to each other to get the final result, to get the final curved inflated result. But for now, it's fine. For each cell, it looks like this. Okay, so this one could be another parameter which we could control. So let's bring it here. gonna drag and drop. How do I name this? Height for outline inflation. It's a long name. Maybe I don't like it, but I'll just keep it like this for now. Okay. Now that I have a curve inflation, it's time using this to inflate the surface as using this as a guide. Okay, just inflating the curve might be fine for some of you. It also looked like a bubble in the end, but I think it is interesting to make the surface looks inflated. So especially for rendering some stuff like that. So that's what I'm gonna do. Okay, to do the inflation for a surface using this as a guide, I'm going to bring the surface information, which is coming from this one. And I'm going to do the same subdivide by just copying this subdivide node here. Okay, and just need to check if the point position on the edge is also sharing same as this one, the point position over each line same as this subdivide edge position or edge point position. You can see that it shares the same position like these, and that's the important part. Okay, now what I'm going to do is to using this as a guide, I'm going to move the edge of this surface or edge of this subdivide surface to this goal edge. This is the goal edge of the outline. Okay. So let's do this. I am going to use the, in this case, point wrangle, I guess. So what I want to do is to move the edge of this cell using this, this as a guide, because this shares the same position with this one and this one on the edge. You can kind of get the corresponding point number for this point for each edge points, and use the point number of this curve. You could actually use that to get the goal position out of this inflated curve. So connect this to a third point, third input. And finally, by combining all those informations, you can actually move those edge of this surface to this outline point position. Okay. Hopefully it makes sense. So first, you try to get the nearest point information from the second input, which is these edges. New point, and get the point position. And what you want to get is the distance between the current surface point position and this resampled point position. And if it's equal to 0, or if it's really close to 0, then that means the point we are looking at is on the edge. But that should be moved. So calculate the distance, between the current point position on the surface and the edge point position. And if the distance is close enough to 0, I'm not gonna say equal to 0 because we are dealing with a computational geometry. There is some number errors, so getting an exact number is pretty hard in computational geometry. So gonna make sure it's some you're gonna have some kind of threshold. Okay, so if it's small enough to equal to 0, then you are going to move the current point position to this point in position, which is point from second point position, second input at the NPT. There you go. So you have just moved the edge point to this inflated outer point position. Okay, now after doing this, I'm going to use something like a smoothing or Laplacian smoothing to create the inflation. And when we try to use that, I want to fix the point position of this outline. I only want to move the points inside the surface, not on the outline. So I'm going to give an additional attribute like weight. If I don't want to move the point, then I want to make the weight to 0, since this is the outline point. The one that should be moving, I'm gonna set the weight to 1. Okay. And outline point position transfer or something like that. Okay. Now it's the time I move each point inside to a normal direction, then do the inflation, do this Laplacian smoothing again and again for several times to get the inflation effect. So to do that, I'm going to create another for loop inside, like using for each numbers. Doesn't have to be too many times, maybe like 5 is fine. And I'm gonna make it as a feedback each iterations because I want to make a recursive loop. And for input, I'm going to use the fetch feedback. Okay, now things that I'm gonna do here is pretty simple. First, calculate the normal, point normal for each point. Okay, and use some simple function to move each point to a normal direction. So I'm gonna use the point wrangle. And I also need to make sure if the weight is equal to 0, the point's not gonna move. So and I also want to make the center point to go further. The points which is close to the outline moves slower, so that I could have kind of a mountain-like shape somehow. So in order to achieve that, I need to think about how we could do that. In order to do that, we need to know how much is this center point, or each point is far away from the outline. Okay, so how should we do that? Let's see. And also the lengths of the neighbors, the lengths between at each point and the neighbor points might be also important, because if you look at this surface and this surface, you know, you see that the length is a bit different. This is smaller, this is larger. The larger lengths must have more inflation than the smaller lengths. Especially like these part, you have a small number of lengths, small lengths on a neighbor edge, which you could assume that the inflation is a bit smaller compared to the one you have right here, where the neighbor edge is really large. So maybe we could use that information as an amount of inflation here. And yeah, let's try to do that. Let's try to just use that as a information to move the surface. So to get that, I am going to get all the neighbor points from each point and try to calculate the lengths between the current point and the neighbor points, calculate the lengths for each edge, then just get the average. So loop through all the neighbors. And get the neighbor point position. Calculate the distance. Since I want to calculate the average, you can have the empty variable here, starting with 0. Add the distance to the average distance. Finally, divide the average distance by the number of neighbors. Then you get the average distance, or average edge lengths on each point. Okay, now I could use this as a weight to how much you offset each point. Let's see. So I'm gonna offset the point to the normal direction by, first of all, weight if it's equal to 0, meaning if it's on the outline you don't want to move, and also multiply it by the average distance that you have just calculated. Let's see what happens. Okay, so not that bad. There are some interesting artifacts coming here because it's being self-intersected, but that's fine for now. Now you might want to also control how much it inflates as an initial step. So let's multiply the inflation value. Like that. Okay. And then the first step might not give you a clean result, so I'm going to create an attribute blur to smoothen out the surface a little bit, and using the weight so that if the weight is equal to 0, the attribute blur is not being affected. Okay. And let's keep, so the balance between the blurring iterations and this inflation value and the number of loops is pretty important, I think, here. Now this is inflating too much, I guess, by using 5 loops. So if I increase the number of below iterations, it drastically reduces the surface inflations. Let's say I want to keep it to 10. Now the inflation is not enough, so to make this more inflated, I could increase this initial inflation steps a little bit more. So I'm gonna go back to inflation, make this maximum to 20 or something. See what happens if I increasing this value. Okay, now starting to see a better result here. Now if I set this attribute blur steps to 5, the amount of inflation could be smaller. But this is going too wild here, so maybe keeping it to 10 gives you more option how much you want to inflate. So that I could make this maximum like 50 or 40. I'm not sure. Maybe this is too much. But just in case you want to have an exaggerated result, let's make the maximum 40. Okay. Okay, so that looks good for a single inflated result. You are keeping the edge, the outline to be fixed. You're just inflating the inner surface like that. And the single cell itself, it doesn't really look natural. But once you combine all the cells together, which you will see something like this one. Currently each cell is being intersected to each other, so you don't have a clean wall connection, but by trying to relate the same point position on the surface on an inner wall and try to get the average point position, you'll get the clean curved inner wall shape in the end. So let's hope for that. Now let's try to promote the parameter that we have set here. That is for the surface inflation. Okay, so height for surface inflation. It might be a good idea to also control the number of steps for these loops or number of attribute blur, but that's gonna make parameters too much or too many to control, so I'm just gonna keep this as an only parameter to control. But if you willing to control these values as well, I think you could also do that. Okay, so now I have several parameters to control the single inflated shape. It's time we think about how we relate each wall, inner wall, together so that we could have an average result. Okay, so to do that, and again, another things that I need to set is the how much is the bubble is strong, how strong the bubble is in terms of the pressure. When you have multiple number of bubbles like these, you want to compare each bubble next to each other to say which bubble is stronger, so that which one pushes harder to create the curved wall. You have, for example, you have, in this case, you have this cells and this cells. If you get this together, so you have two cells together, and somehow in order to have the shared wall, you need to push and pull the surface based on the inflation that each one has, and this pushing strength or pulling strength has to be based on some values, and that could be based on the volume of each cell. If the cells is smaller, maybe the pushing strength is smaller, weaker, so that you have smaller wall. If this is bigger, then it's obviously it's gonna have to push it more to have more curved wall affected by this shape, and this is being pulled or pushed by this one. So to find the balance between two connected or two neighbor bubbles, one of the things that I could use is the volume to push each other. That's what I thought in terms of proceduralism. So let's try to calculate the volume for each cells here inside for each node. I could just do that by using measure node. Measure node, calculate the volume, and again I'm gonna use the per piece per cell PT, so that each primitive shares the same volume. And actually in the last, what you want to move is the point, so you could promote this volume information to each point. So I'm going to use an attribute promote to promote the primitive attribute, the point, and the attribute name is volume. And let's try to keep the primitive as well. Yeah, this has to be the volume. Okay, so if you look at the point attribute, yeah, you get this new point attribute called volume, promoted from primitive. Okay. Now's the time you want to get the average point position to share, which shares the same wall positions. And to do that, we need to have that kind of a ID information, which point stays on which wall. So to do that, you need to have that information somewhere. And to do that, you need to, for example, for this shape, you need to know what this point ID is, and the point ID of this point here, which also appears on the other side of the cell. So there's supposed to be a cells here as well, and this cell also has this point, and that point must share the same ID in order to create the average point position between two points which shares the same ID. So in order to have the single ID for single points or connected points, you need to have the guided information, guided geometry, and actually this is the guided geometry that I was already making it. Now this is the bunch of Voronoi cells that's been subdivided But currently the number of points on the inner wall is duplicated because you are subdividing for each point. But by fusing this final geometry, you can actually fuse the duplicated points on inner wall, like this one, as a single point. Okay, meaning you only have one single point information for each wall, which means you can use that point number information as an ID, a unique ID to be used with these each cell to share the same ID. Okay. And as an additional information, what I would like to have is to determine which cell primitive is on the on which wall. Meaning I also want to have an ID for each wall information, like make this Voronoi wall as one ID, make these Voronoi wall as one single ID, which also could be useful later. So I want to have that information as well. So let's do that. To do that, what I could do is to try to have a single-sided geometry out of this output. Meaning if you are having a duplicated surface, for example on the inner surface, you are currently have duplicated surface in and out like these. So by removing one of the surface, if it's been duplicated, then you could have a single surface. And by having the single surface, you could have a single ID for each surface, probably. Okay, so that's my plan. So let's do that. And to do that, what I could do is to give another guide information for each surface. And looking back to going back to this information here, let's reset the viewport. Okay, sorry to hear that. So first of all, I could calculate the centroid for each surface here, which will give you a center point of in each surface. So which means I could use a simple function like primitive wrangle, give a center point, remove the current primitive, like that, and use these points as a guide to determine which surface is on which point, or use this point as an ID. Now this point is also being duplicated, so you could use a fuse to remove the duplicated points. So this is the total number of the Voronoi walls. Okay, so center of surface, and fused, and use this point as a guide to determine which surface belongs to which single surface. Okay, that's my plan. Now that's when you are using this pnum actually, and maybe I need to connect it here. So for each point, I probably need to bring the p number informations. So currently I have these p number, which is derived from the primitive number. Then by using this, let me think if I need to transfer the p num. Maybe not, maybe not. Think. Let's think. What I just want to do is to relate the single surface, and these points are represents the single surface information, which currently I have 210 points, and I need to really set each surface right here, get the information from this to know which surface belongs to which points. So let's see what I could do here. So I think I need to have some additional information here. Yeah. When I create the point, I'm going to pass the primitive number that is being attached to the primitive. Like this, which will give you a point attribute like this, which is related to this one here, pnum, which is the ID of each surface here. Okay, now the problem here is if I use the fuse, some of the pnum is gone, so maybe that could be a problem. Or maybe yeah, okay, I think I got it. So let's say this is the guide, and going back to here, and for each primitive I could check if the pnum which exists in this node I want to check if the pnum for each primitive here, which is this one, exists here on each point. If it exists, you can make this primitive live. If the number doesn't exist here, if the number on each primitive on this primitive node on this fuse node doesn't exist on the point rank from this node, then you can delete it to keep the pnum on primitive here and pnum on point attribute here the same. So I could check for each primitive referring to the point attribute of the second input here. And I could say find the pnum or point number by using a find attribute val from second input point. The number, the attribute is pnum, and using the current pnum from the primitive. So if you couldn't find the result, you get -1 as a result, meaning that's when you want to delete the current primitive. If you have the value more than 0, then that's when you could keep that primitive. So if pt is less than 0, then you could remove the current primitive, so that you could you only have the single-sided face. Okay, let's check. So previously you have 7,282 surfaces, and now the surface has been reduced, and you should only see single surface face here. Previously you had duplicated surface here and here. Both. This part is easy to see. You are seeing some Z fighting faces, but if you should if you are only getting the single surface, then you no longer have Z fighting. Okay, so I think this is working. And now you get this single surface here. You can actually use this as an ID. An ID is, in this case, is this pnum. Pnum could be the ID. Okay. Hopefully that makes sense. Maybe not, but yeah. And that's what I'm gonna use as a guide. And finally, I'm gonna try to fuse this again. Maybe this is not necessary, but just to check. Okay, might not be necessary, but just in case. And now, in order to use this as a guide to create the ID information for each point on each cells that I have here, I could use a point wrangle and referring to the overall geometry with an ID information. I'm going to transfer the P number or actually I could just transfer the point number itself from the surface using as an ID, because what I just need is the related point position for each inner wall. So the point index, it could actually be a point number from this surface, because there are no duplicated points here. So int index is equal to near point P. this could just be an index. Now, in terms of the p number, I could use it later, actually. Okay, now going outside the loop, it's time we use the pressure to create the average surface position or average wall to get the final result. This is the final step. And here I'm going to use a point wrangle. With pressure. And here I think I could also use some information like index, probably, not sure. Let's see. Yeah, I think I could use the ID. Let's see what kind of algorithm that I need to implement here. So this is the final step, and things that I need to do here is trying to get the average. For example, you have two inflated cells, and somehow you want to create the inner wall to have the final bubble shape like this. And in order to do that, for each cells which shares the same point index, you need to move correspondingly so that in the end the final point position shares the same point position for a connected piece. So to do that, you need to know how much you move for each point based on what kind of value. Now, first value could be a volume. Based on the volume, you could change how much it moves to which direction. Okay. So let's think. So if you have something like that, something like these, and these intersections, somehow the final point position must be somewhere in between these threshold. So you need to kind of use a function like lerp to find the best result. So the value has to be from 0 to 1. And if you choose the 0.5, then you get the straight divided curve, which is gonna make a flat wall surface. And that's pretty boring, and that's not related to volume or pressure. It doesn't really look realistic. So you need to find the best value for this one, how much you want to go, what's the best threshold based on the volume. So let's see. First thing first you need to for each point you need to find the target. I mean, if you are looking at one of the point of the cell like this one, for example, if you are looking at this point here, you need to know which point corresponds to this point. In this case, one of the point from this cell has to be corresponded or related with this point here. So you need to find those pair. You need to find a pair point for each points which is on the inner wall. So to do that, you need to know the index. You need to know the other side of the point number. Okay, so that can be retrieved somewhere, and that is I think it's this one here. This is where you have created this is where you are getting the index information here. So you could actually wait a minute, let me think first. Maybe that's not the case here. Let me see. Maybe that's not the case. In order to find out the pairs, you could actually just do it right here by itself. If you look at the point wrangle, point information, if you look at the index, some of the point index share the same numbers. Like if you have 3 points, then that means the points should be on the corner. If you have 2 points, that means you have that those points are on the inner wall. If you have no duplicates, then that means that's on the outside of the bubble. So you can indicate which point belongs to which positions by looking at how many duplicates you have for these index. So having that information, you could get all the corresponding point informations out of each point by finding out the point index information which it shares with the same current index value. Okay, now if you're sharing 3 indexes, if there's 3 duplicate indexes, you get 3 results here. If you have 2 duplicates, meaning if you're on the inner wall, you get 2 values here. Now you can loop through all those information and try to get the average based on, not the average, but weighted average positions based on the volume. Okay, so in order to get the volume, I think each point also have its volume information derived from the primitive. Let's check. Yeah, this one. So you could kind of use this one as a weighted value. So going back to the geometry or scene view, going back to here, let's get the volume information from each point. At PT, let's also have a variable called total volume. And starting with 0, sum up the total volume with this volume here. Then try to find out the weighted position by multiplying the position by a volume, and then may sum up to a, I don't know, average position attribute or variable. So average position being added up with these volume positions multiplied by the volume. Then finally divide the final average position by the total volume. You get a weighted position based on the pressures, or I mean the volume. So I'm assuming the volume is equal to the value of pressures. But maybe you might want to change this volume value a little bit based on how much it affects. The small difference between the volume might affect a lot, so let's give a chance to control that by using a power function with your choice of power. Starting with 1, I think, as a linear value. Okay, now you have this average point position. You can now update your current position with the average now you see that the intersection is no longer available, and if you also look at the interiors, somehow you get these non-intersected result like this. Previously it looked like these, but now look like these. Okay, now it's time to play out with this inflation power or volume power here. Currently it is equal to 1, but let's say how much it changes by changing this value. So if I increase this, the small difference of volume will affect a lot based on the pressure, based on how much it pushes out the inner wall. So by increasing this power, you can see that the curvedness of the inner wall is increasing because the small difference between the volume, small volume difference between each cells will drastically affect the pressure. So that might be interesting. So let's keep it like 10 for now. I'll give you a really rounded shape inside. Okay, now it's time I could make it a bit more detailed or smoothen out. currently it's a bit too low res. So here finally I could use something like subdivide. But the problem here now, I am having these kind of spaces here because the subdivide actually smoothen out the shape, which is okay for the outer shape, but not okay for these intersections here. I don't want to have a gap like these. But if I check this, doesn't really affect, it's no longer affecting the outside surface anymore. So you need to give this subdivide for each single surface, or not per cells, but per surface, per walls, outer walls or per inner walls. So to do that, you need to kind of split each cells into each surface. I mean each walls. For example, if you have a thing, if you have a cells like this, if you just use subdivide node, you're just smoothing out everything. But I want to keep the outer edge fixed. Just want to smooth the inner surface. It doesn't do that, and it doesn't even do that if I increase this weight. It just also crease the outer surface as well. So that's not the effect that I want. So in order to achieve what I want, I need to split each surface, each walls into separate group or unconnected group, unconnected surface, so that I can apply subdivisions for each walls. And to do that, I already have an information to do that. That is this pnum. This pnum indicates the number for each surface, actually, which I have been doing right here. So I can use that to divide each surface separately by using for each named primitive use pnum. Then I can access to each surface here, which is not shown here. Let's reset the viewport like that. Now I don't really need to do anything inside the loop. I just want to split the surface, so just having a loop like this is fine. Then use the subdivide again. See the result. Now you no longer having the gap on the corner or inside, but you're fixing the edge, but at the same time you're smoothing the surface. That's the effect that I'm looking for. Okay. And if you try to see the inside, okay, sometimes let me reset the viewport. If you look at the inside, you're seeing a crisp edge with a smoothed surface. That's what I was looking for. Okay, so that's the final result that I wanted. Now I could set up a simple viewport rendering. and viewport shading so that I can see through the bubble clearly to see how it really looks like inside. So I'm going to create a material node. Create some simple principal material, principal shader. Base color to anything you want. Just want to make the transparency really high. Just to check how it looks inside. And apply that material like that. Now maybe I could change the color to white so that I can see it a little better inside. Okay, so that's how it looks like inside. Really bubbly here. Now going back, and if I change these power, the pressure power here, if I make it 0, you could see that the surface becomes really, the inner surface becomes really flat, just like you get from the Voronoi output. Which might be okay, but having more curved surface, I think, looked more natural for bubble, or it looks cool and visually nice, at least for me. So that's why I thought it's necessary to set a threshold like these, or pressure like these, to make it a bit more natural. Okay, I think it looks nice. And combining with the animation, it's gonna looks really nice. Now it's a bit too slow, so let's cache this a little before playing it. I'm gonna use the file cache to cache the animation. Doesn't have to be really long, so until something like 80 frame is fine, I think. So let's cache this. Okay, well, meanwhile, this is pretty much the end, so if you have any question or if you have any feedback, I see one of you didn't find it helpful, so that's okay. But if you have any questions, let me know. Or if you have any more idea how this could be improved, or if you have any other way which you could use to have the similar result, that will be really helpful. So let me know if you guys have any feedback on that. Thank you, John Doe, for kind word. Okay, the cache is done, so let's see. Let's play out. So this is how it looks. Nice, isn't it? Now, if you want to get just the outline, you could also do that. You could divide. You could use the divide node. Remove the shared edges. use the poly path. And there you get the outline. And this is also interesting to see. Initially, I was just trying to create the lines, but I found it a bit boring just to see the edges. So that's why I'm looking for a way to create the surface as well. And it turns out doesn't look that bad, right? Hopefully you find it interesting as well. Yeah, so that's how I did it. And if you use like render like Redshift, it's gonna give you a nice rendered even inside with a refraction or reflection. So hopefully you will try that as well. Now let me try with other kind of base geometry other than spheres and see how it looks like. Maybe a bit more large number of points. Okay. Let's see what kind of test geometry I could use. Maybe I could use something like human, template body. Not sure if this is suitable for, but let's see. The problem could happen on these thin surface areas because it's a bit hard to create the clean Voronoi structures. So maybe I'm gonna try with the, well, anyway, why not just try it? I'm gonna create the switch node. Connect this to human. See what happens in the result. Oops. Okay, I'm getting an error somewhere. And that is because, okay, so this is why. The Voronoi fracture is creating some result that's not pleasant. So that's why. And the reason why I'm getting here is because some of the process are making the unsubdividable surface. So that's why. So maybe I could either create a error passing function if one of the primitive is not able to subdivide, then skip that geometry or just try to increase the number of points so that you don't get errored surface. Let's try that first. If I increase the number of points, in this case maybe like 200, does it give me result? No, not yet. Might gonna take some time. 500. Still not. So maybe I need to create some kind of a error passing functions so that even if the geometry is not being created for some mesh, I guess, yeah, these part where the finger is having problem. And that is coming from which part? This part, I guess. Yeah. So either you wanna increase the number of points or just ignore those broken pieces. So to determine where it is broken, where can I check it? Where can I check? What's this? Okay. I could probably delete the geometry which is not suitable for calculations here, right after here, I think. So I could kind of assume if the volumes is equal to 0 or nothing, then that's where you want to delete. So for each cell point, yeah, probably somewhere around here, I'm gonna calculate the volume here. Volume per piece, cell PT. Let's check how it looks like. And so if it's close to 0 or negative, that means it's not being closed, I guess. So those volumes could be deleted, I think. And if it's really close to 0, that could also be deleted, I think. So let's try doing that. Delete if volume is less than 0.001, 0001, delete it. It's deleting unnecessary stuff. Maybe determining the volume, determining by the volume might not be a good idea. I guess I shouldn't calculate the volume here, but before fusing it. Yeah, this should be it. Okay, now, yeah, this makes sense. Now I could, oops, that was too much. Still too much. Still seeing those lines here. Maybe deleting by the volume might not make sense. Yeah, that because those line only happens after this. What if I remove the fuse? Calculate the volume here. Delete it. Does this pass the error? Nope. Oh, didn't connect it here. So if I connect this here. Okay, now it passes the error, so maybe this might work. Where should I connect this fuse? I think I should do it somewhere. Maybe here. I don't know. Just trying out. And let's see. Do I get some result? Okay, yeah, I did. Interesting. Bubbly man. And it might take some time, but if you do the calculation like for several frames, you could also animate it on human as well. Just using the sim with the rainbow sim from last week. Okay, I hope you also liked us rainbow simulations last week. The algorithm is simple, but Interesting to see how rainbow works. Yeah. Okay. So you could see that it also works on any input geometry. So probably this could also work on pig head. Okay, nice. So bubbly man is done. Now I have some unwanted points here, probably due to some, I don't know what is happening here. Do I have points on the center? Nope. Where does it come from? At this point, we don't have it. Here. Okay. Seems like I have some unnecessary geometry somewhere up here. Probably where the hand used to be. Okay, well. For some reason, this point is sharing with some points on the center, which doesn't really exist. Funny. Anyway, I don't know if I should fix this because this is a rare case, I guess. But it doesn't really look nice. Crayfish default mesh might be more appropriate. Crayfish. Not sure which one is the crayfish. But I guess I want to solve this. I mean, I at least want to know why I'm having this error here so that it's error proof. Let's see. So at least from until here that was fine, but the problem happens when I'm calculating the pressure result. And that is because I guess this one. I'm trying to find out the nearest point information from each cell here. But there is a chance that there are no nearest point. And why? Okay, why am I losing some of the geometry here? These geometries are missing right after this one. Okay, maybe because of this one, but so in those cases, I think I need to make sure that I'm not referring to those disappeared geometries. So it might make sense to first get the nearest point number, get the point position, calculate the distance, and if the distance is small enough to 0, then you could use the indexes NPT. If not, then set the index to -1. Now let's see what happens. Oops, didn't work. That wasn't the case. Actually, it made it worse. Maybe I'm doing something wrong here. Just want to check now. What if I remove those unnecessary points? Does it solve? Yeah, it did. Maybe this is the one. Okay. Anyway, I should try with more rigid, more thicker surface for sure for this kind of simulation. Squab, I see. Squab also has a thin like tentacles, so might not work, but let's see. Switch this to Squab. What's happening here? Oop. Oh wow. Oh wow. Now okay, this is unexpected. Something happening here. So what is happening here? What is wrong with the setup? Huh. So yeah, it is also deleting those thin places, but somehow, wow, somehow this is not working. Not sure why. Let me try to remove this and see what happens. This is the problem. Yeah, this was the problem, so maybe this is not the correct way to implement. Oh well. Maybe if I have time, I'm gonna fix it later. But for now, I'm just gonna ship with these setup. So once I fixed it, I think I'm gonna upload a minor fixed version as additional file. But for now, I'm gonna just upload the files that I have here. At least it works for some I don't know, at least thick enough geometry, or if you have enough number of points to create a Voronoi. Interesting. Well, guess there is a room to fix, but that's fine. That's good to know. I'll try to do this sometime later, because it seems it's gonna take some time to fix it. So for now, I hope you could find it useful to play out with some limited number of geometry. Like even for a pig head, if you convert it into VDV, convert it back to geometry, might make sense because it's gonna make it a bit thicker. Maybe I could also insert some VDV VDV resample, was it? Nope. VDV reshape. Yeah, this will inflate the whole geometry a little bit. So this might gives you a little bit better result. Yeah, how's this? This might be better. Okay, so instead of having a squab, let's try with this inflated pig head with a small number of points, like 100. Yeah, this seems to work. The ear is being broken, but probably I need like 200. Yeah, starting to get some result. And since I have several parameters to control the inflation, like if I change this to smaller value, you have less inflation. Doesn't look like a bubble, so maybe I need to have at least 10. Or 15. Yeah. If I make it 20, now it's really inflating a lot. If I make this 2 for outline, getting more bubbly, and these looks really doesn't really look like a bubble anymore. It's more like a balloon. Okay, now it looks more like it. So what's good to have is these inner curved wall. That's kind of what I really wanted to show. So hope you liked it. So that's pretty much it. Thank you for watching. Let me just wrap up this session by organizing a parameter a little bit. If I need to change the parameters somewhere. Now just seeing the outline also feels like it looks like a bubble, but it's always nice to have a surface. Okay, so where was I? So I was trying to control the this could be another parameter to control. Pressure, power. So where was it? There you go. Pressure, power. Okay. And if I change this to 10, you have more like pushing strengths. You see the difference? It's pretty interesting, isn't it? I mean, the most interesting part for me is right here. This. More like a grape-like shape. Huh. Forget it. What else? So I have these. Okay. Yeah, that's pretty much it, I think. So that's it. So thank you very much for watching, and thank you for all the comments. Thank you for all the kind words. Like growth, if less transparent, the pig head mesh helps with that thought. Yep. For sure. How would you go about adding geometry in a simulation using this? How would you go about adding geometry in a simulation using this? What do you mean? What do you mean by adding geometry? How would you go about it? Adding geometry. I think I'm not following the question right. Let me know if you could specify what it really means. Say an expanding set of bubble. I see. Increasing the number of bubbles, you mean? That might be interesting. Meaning starting from a small number of points. Adding points gradually, if that's what you mean. In those cases, we could try with the sphere. Guess. And I guess I need a minimum number of points. Not 50, but 10. So if I have less number of points, seems like I need more pressures. Guess I need to find out the balance. If I play it, right now it just moves. So if I want to add more points gradually, then I guess I need to do it right here inside a solver. So let's see. If I want to do that, then let's say per, I don't know, per 5 or per 10 frames add 1 point. Then what I could do is, after updating the point position or before, I don't know, anywhere is fine, I guess. I'll do it before. Point wrangle. So this is, so where should I add the point? That's the question. I could connect this ISO surface to the third input of this solver to use it as a reference, and I could make a detail attribute at new point, and if the current frame per, so I don't know, frame value is equal to 0. Let's say per 5 I want to add 1 new point inside this volume. I could create a scatter node here just to create 1 random points, and don't relax, and use the global C's with frame. So for each frame you get random point position here within this sphere, and refer to that point, and when this condition meet, you're going to look for all the points from the second input get the point position, and then add new point. Okay, let's see what happens. So just want to check how it looks like with the point. So for each 5 frame, the new points will be added somewhere, like that. Okay, now let's see how it looks like with the simulation. More like a frog egg. Maybe I need to add more points. And I want to start with a bit larger number of points. So let's start with 20 points. Right, then per, I don't know, per 3 frame add new point. And let me also file cache it, version 2. Finger crossed. Hopefully we'll get something interesting. What this percentage in the if means? Percentage means modulus, meaning you can calculate the remains when you divide the number. So if you calculate the modulus between 6 and 5, that means you are dividing the 6 by 5 and you get the remains 1, and that 1 is the result of the modulus. So if you try to calculate the frame by the modulus of frame by 5, then you are looking for the and if it's equal to 0, that means if you divide the frame by 5 and if the result remain is equal to 0, that means the frame should be either 5, 10, 15, 20, 25 and so on. Let's see the result then. Hey, not bad. Interesting. All right, that's good. This is good. Thanks for the idea. Nice idea. Think I like it. Think I like it. Yep. Okay. Good to know. Yeah, suddenly it becomes more cell divided, some kind of an egg shape. Not like a bubble, like more like a egg shape. Egg, but nice. If I just see the outline. Cool. All right. This was nice. Okay, so I think it's time for me to wrap this up. Let me also have the final parameters that I have just added. This extra adding parameters. So add point per frame. How do I explain this point? Frame. No. Just gonna explain it. Not a good explanation, but you'll get it. Okay, so I guess that's it. Yep, I think I've enjoyed the session. Thanks for joining with me. I'll next week I'm going to do the the shortest branch growth, which runs on inside the typology or text, which could be also interesting. So if you could join, that'll be great. So that's it for today. Thank you very much for coming, and thanks for all the comments. I'll as always, I'm going to upload the file that I've just created here to a Patreon page, so you can, I am gonna paste the link to the video description so you can go there to download it for free. Right after, I'm gonna upload it right after I finish the live stream. Yeah. And if you are feeling like it, if you could support me on Patreon, that would also be great. But it's your choice. The files is all free, so if you could enjoy, that would be great. So that's it. Thank you very much, and good night. It's 4 a.m. in Japan time. I must sleep. Okay. Night.